computer science professor said in class one day when he couldn't get a device to work correctly, he's like, God, I hate computers. Like, and I know what he means. I finally understand it. So yeah, computers are so central to everything that this class is going to be about that we actually kind of need to talk about them in some. We need to talk about the internet on some level. I'd like to build kind of a baseline knowledge base for what the internet is and kind of how it works and what some of the different components of it are. So we're going to try to answer the question, what is the internet? What is the World Wide Web, and what's the difference? What's the difference between analog and digital data? And what is a protocol? And what is a domain? And again, not in any really like nitty gritty detail, but from a really high level view. Like just what do they do? What are these things? And just in really general terms. My goal is not to build expert level knowledge, but just to get everybody kind of on the same page. So what in the world is the internet? One thing it is not is a series of tubes, which is I think some politician, I can't remember which one, maybe it was George Bush Jr. said that, something about it being a series of tubes. It's a global network of computers. And if you're in this Zoom meeting, the computer that you're using, whether it be a smartphone, tablet, or laptop, is part of, not just logged onto, but it is part of the internet. You have an IP address that is connected to the internet. You're sending packets. You're part of this network, this ecosystem. So it's, in reality, kind of like this network of networks of computers. They're all linked together and they all speak the same language. On some level, they all have to talk to each other. You know, if I want to talk to a specific computer on the other side of the world, my computer has to be able to find that computer in some way. So all the computers in between all have to kind of be speaking the same language. It operates on this concept that we call packet switching, which we're going to get to in just a second. But let's rewind. Let's go back in time to like when my dad was a kid. I never experienced this kind of telephone system, but we did have a plain old telephone system. When I was a kid, this is all we had. The ARPANET was a thing. The early days of the internet were already underway when I was born. I was born in 1980. But the home computer, the PC, was invented in like 1981. So it was like a year after I was born. So the POTS, the plain old telephone service. This is how it works. See this picture, this lady here, she would sit listening. And so person A, let's call her Alice, wants to talk to Bob. And then she picks up her phone and then hits the little lever a few times. And it rings at the operator's end. And she would say hello, and then hello operator, and then they would say, yeah, I'd like to talk, and Alice says, hi, I'd like to talk to Bob. And she's like, okay, one moment. And then the operator will plug into Bob's port and then ring the phone at his end. Bob picks up the phone and she says, hi, Alice wants to talk to you. And he'd like, okay, I'll talk to Alice. And then she takes another cable, plugs the two of them together, and then they have a dedicated line where they can connect. That's literally how it worked. So what they found out, or what we've known all along, is that human sounds are transmitted via phone lines using what's called an analog signal, meaning how your voice, the pitch of your voice, the volume of your voice, all of those things are transmitted by varying the voltage on the wire. So the voltage that's going through that wire changes based on how your voice is inflected. It's a very smooth kind of freeform thing. There's nothing digital about it, at least back in these days. It was just electricity, voltage, and my voice vibrates a magnet in the microphone, which sends a signal down a wire, which gets to the other end, and it vibrates a little magnet inside of the speaker on the other end, on the other phone. What we found out was what they actually found out was these information theorists thought, Well, this doesn't use that much signal. There's not that much signal being used. We might be able to get more signal onto a telephone line. And by doing research into this, they found that they could actually get more signals on a telephone line if we sent it digitally. We could have more than one signal on one telephone wire at the same time if we didn't restrict ourselves to analog. So they developed new ways of transmitting data. Now, one of the things is that we need to understand is that, especially with new high-speed fiber optics, is that only one thing, this actually works better if we're all in the same room, because then we can talk about how the room's network works. But say you have like a wireless access point. Oh, someone's chatting with me. Oh, okay. Sounds good. So this concept of packet switching works like this. I can talk to, let's pretend we're all in the same room, right? I can talk to the wireless access point, or my phone can, and yours can. We're all connected to the same wireless network, but only one of us can actually talk to it at a time. Like it keeps a line. It keeps it says one at a time, please. So we're all shouting at it, but it sends out a message saying, okay, now it's your turn to talk. Okay, now it's your turn to talk. Okay, now it's your turn to talk. But it kind of feels like we're all doing it at the same time. We could all be on the internet at the same time. We could all be watching YouTube videos at the same time. But in reality, only one of us is talking at any given time or receiving. And this is done because what we do is we take a large piece of information, a file, a video, whatever, and break it up into tiny pieces. This is what we mean by packet switching. One person is talking at a time, one person is listening at a time, and we take turns. And it happens very, very fast, like millisecond increments. Like we're talking thousandths of a second. You get a thousandth of a second to receive one packet, and then the next person gets to receive their packet. So there's 26 people in the room. We each get to receive, a few hundred packets per second, even though we're taking turns. Next. So a packet is a bundle of bits, ones and zeros. It's a digital signal. It's either on or it's off. And it's like the coolest, easiest way to communicate because there's no ambiguity. There's either voltage on this wire or there isn't. So it's a bundle of bits that a sender wants to send to a receiver. And the question is, how do we do this fairly? How do we make sure that everybody gets to talk to that router in a way that's equitable? And how do we make sure that all of the information that we want to send is actually going to get where it's going? If I'm trying to download a meme or a movie or whatever, how do I know that the entire thing is going to get there? Like this is an insanely complicated feat that we've accomplished, being able to do this apparently without even having to worry about it. So we want to send a lot of data. How do we take it apart and put it back together again? And this is why we have protocols. This is what a protocol is. A protocol is a set of rules. We developed a whole slew of them. There's probably a couple of dozen protocols that operate on the internet, but there's three really important ones we're going to talk about today. At first, they're pretty simple. Back in the 70s and 80s, they didn't even have security built in. There was no encryption. There was nothing like that. Nowadays, we have pretty much everything is encrypted, and they warn you in no uncertain terms when it isn't. Like the LLTC website does not have a security certificate. It's not encrypted. So we have a collection of protocols, and let's talk about the most important one first: the Internet Protocol. Go figure. It's called the Internet Protocol. IP. You've heard of IP addresses. Its job is addressing and routing to make sure that it's like taking an envelope and putting an address on it and then sending it off. Only it doesn't work like if I send a letter to the cities, it's pretty much going to follow the same route every time. Or if I'm going to work, I'm going to follow the same route every time. Or maybe I'll take the scenic route. IP addresses, but like Okay, yeah, we'll get to that point in just a second. IP addresses basically roughly translate from domain names like google.com, LLTC.edu, amazon.com, whatever. The website domain name translates into an IP address via a mechanism called the domain name service, which was implemented as a concession to the fact that humans can't remember all the IP addresses. I used to memorize all my friends' phone numbers. I don't do that anymore. I look them up in a dictionary, which is literally exactly what domain names are. It's just a phone book. So usually a packet, like I take this picture apart, like this picture of Frodo here. This picture got taken apart on my computer and then sent across Zoom to you guys. Oh, yeah, this picture right here got taken apart and then sent to you and loaded on your computer, but it didn't get sent as one piece. It got sent as a million, or 1,000 little individual packets. It got torn apart and then it got reassembled onto your screen by and each one of those packets didn't follow the same route. They probably took all sorts of different routes. The internet has all these mechanisms in place to prevent congestion, like to prevent traffic jams, to keep everything moving smoothly. And it all works by some sort of miracle. And it is kind of a miracle. There are two versions of the internet protocol currently in service, IPv4 and IPv6. I believe if you're in our region, you're probably still using IPv4. Paul Bunyan, I don't think, has version 6 implemented, and I don't think Midco does, at least not in this region yet either. So you're probably using version 4. They're trying to roll it out. Let's get my laser pointer out. So that's the internet protocol. Its job is addressing and routing, making sure that the packets follow the right route through the internet to get where it's going. The transmission control protocol is a little different. Its job on each end is to break the message apart into pieces and then put it back together again. So this is the part that does the puzzle. It takes a message, tears it apart, puts it together, and presumably in the same order. And it really, really works pretty well because it has to acknowledge every single packet that gets received. So I send packet 1, 2, 3, 4, and then I have to wait for the receiver to say, "Yep, I got packages 1, 2, 3, 4." So it's like there's several steps. I think it's like 4 steps involved in sending even one packet to make sure it gets there. And if it doesn't get there, it has to be resent. There's a pretty strong guarantee in TCP that it will get there without any loss of packets. Unless there's some sort of major error, it will get where it's supposed to go. And the TCP is also responsible for congestion control. Basically, it times the how long it takes to get the acknowledgement from each packet sent. And if that time is getting kind of long, like on the order of seconds, it stops sending packets quite so quickly. It slows down the transmission, which helps everybody. It's sort of like a community effort to make sure that there are no traffic jams on the internet. There are other protocols at this layer. Like instead of TCP, you can use one called UDP, which doesn't guarantee that all the packets get there. It's just the fire and forget protocol. And that's usually used for like video streaming. It's probably honestly what we're using here. But TCP is much more common because that's what the World Wide Web uses. So let's talk about the World Wide Web. What is it? It is not the internet per se. If you look at the internet as a big circle, the World Wide Web is part of that circle. It's like one slice of that pie or one circle within that Venn diagram. The internet is this large computer network. The World Wide Web is part of the internet that we access through a web browser. So like Google Chrome or Firefox or Internet Explorer or Edge, Safari, any of those web browsers that you're using, that is what the World Wide Web is. And the World Wide Web has its own protocols. In this case, we have the Hypertext Transfer Protocol. Hypertext is a way of specifying how web pages are transmitted, requested, and how the errors are handled. There is a secure form of it that's encrypted called HTTPS. It's basically the same thing. It just has a couple extra steps involving encryption. So to that end, the World Wide Web is, I should have flipped these two slides around. Oh, there's a couple left. So this is the part of the web that we navigate through a web browser based on this concept of hypertext, which is basically this idea that you use links to get from one place to another. I click on a link, it takes me to another page. A really great place to get a feel for what hypertext is Wikipedia, because you can click on many, many links within many, many pages. Some people play games. There's a game to see, get a random Wikipedia page and see how many clicks it takes you to get to, usually World War II is the one, because World War II is one of the most extensive Wikipedia articles. How many links does it take you to get to World War II? And most of the time you can get there just by clicking on a like a very few links. It's like organized like a web, and it embraces this concept of hypertext. HTTP, like I said, is the primary protocol for the web. And it was invented in 1990 by Tim Berners-Lee, a British scientist who locked himself in a room in 1989, didn't come out till 1990, and he had invented the web. And now it's basically the primary way in which most people communicate via the internet. It's heavily dependent, because we're humans and we can't memorize IP addresses, on this idea of domain routing. So what is that? A website's address, like google.com, isn't really that website's address. It's more like an entry in a phone book. Your computer, when it tries to go to google.com or itech.airkuha.com, it asks a server called a domain name server, the DNS server, what is the IP address for that website. And then that DNS server returns a result. It just looks it up in a table, like a phone book, finds the phone number, the IP address, and sends it back to your computer. You never see the IP address. You've never seen this IP address in your life. But this is the IP address that the textbook for this class is located at. If you go to this IP address, you'd find it. You can't technically type it straight into your web browser because of the way my hosting service works, because we kind of every website that's hosted on GitHub shares the same IP addresses. So technically you can't get there with just this. You have to add some more junk on the end of it. But this is the IP address where my server is, or where my website is hosted. So these URLs, Uniform Resource Locators, these are how we locate resources on the internet. Every resource on the internet has its own unique URL that leads to it. The page in the textbook that has much of this information is here. So this is kind of what a URL will look like. You start with the protocol, which most web browsers hide these days. Let me bring this up here. ITECH. If you go to this web page, what is the internet? Yeah. So notice the protocol is hidden here. If I click on it, then you'll see it, HTTPS. But most of the time it's hidden. It hides it. The only reason you know that it's HTTPS is they'll have this little this little padlock icon that says that the connection's encrypted. The :/ part is just, I don't know, Tim Berners-Lee's cruel joke. I don't know. It's called a delimiter. It's just the thing that separates the protocol from the rest of the URL. That's it. It's just some characters, a colon and 2 slashes. I don't know. I don't know why he chose that. Ultimately, it's a pretty arbitrary choice. It's fine though. It does the job. Then you have your top level domain. So we have .com, or I bought a .com domain. What are some other top level domains you guys know about? Anybody can think of some other top level domains? There are several. There's actually hundreds, but there's some pretty popular ones.
.org.
.org, .gov, .edu. There's tons of them. There's a link in the text to a listing of all the of many of the top level domains, and they all cost different things. .com domains are $12 a year. .orgs are $12 a year. .net same, but some of them are like $70 a year. I think .io is like a $70 domain. Sometimes you have to buy a domain from somebody else that already owns it, and then it can be more expensive. But if you're buying it straight from the registrar, a .com domain is $12 every year. So this is the domain that I bought. I bought the exclusive rights to put anything on erichuha.com, and I registered it through Google. Google's domain name, Google is a domain registrar, and so I register it through them. They register it through IANA or whoever handles domains as a international regulatory body on domain names. And as a part of that, I can register as many subdomains as I want under that. And so ITECH is a subdomain. So if you go to just erichuha.com, I think you just get my resume webpage, which I need to update. And so the subdomain is it goes to a different server even. itech.erichuha.com is the subdomain, and I can make as many of those as I want, and they can point to totally different hosting services. It's kind of fun. Everything after that, so the domain part is right here. This is the part that translates into some IP address. And then you put a slash at the end of that, and everything after that is the path. So that's like, once I get where I'm going, once I get to the server I'm going, where on that server is the file that I want. So I want this file. What is the internet.html? That is, it's in, I have to go to this folder, then this folder, and then it's in this thing. And so that whole thing is a URL. This is kind of like give you a kind of a sense of what all goes into this whole process. You'll notice a lot of websites have www right here instead of some other subdomain. www is a subdomain. They just usually make it the same as if you didn't have a subdomain at all. But usually, I think by default it just goes to whatever the root domain is. But you can define it to be something else. Like, you're not restricted in any way. It's just not a good idea not to, because people have an expectation. Anyway, any questions on this stuff? My goal is not for you guys to be experts, but it is to give you kind of a sense of a few of the basic terms that are involved in this whole thing. The quiz next week will be largely vocabulary based, like what is a protocol, what is the difference between IP and TCP, those kind of things. Those will be on the quiz. So if you go back and look at the text, look through these slides, you shouldn't have too much trouble with it. Any questions? Anything like burning desire to know something about the internet that you didn't know before? All right. Well, I'm going to get rid of you and bring up my web browser again real quick. Boom. And stop recording. Edu. Raina said edu. Stop recording. Boom. Okay.